I can introduce Beatrice. So Beatrice Pelloni, she has had positions in a number of places, most recently first Imperial College, then University of Reading, Heriot-Watt for 8 years, 10 years, something like that. Eight. Yeah. Okay, so I was the. So it's a great pleasure to introduce Beatrice. She's going to talk about jumps, cusps, and fractal profiles.
Thank you.
Please.
Okay, first of all, thank you very much for the invitation to the organizers, and also for all the work they put in organizing this day and this program in general. It's been clearly much worse than they expected it would be, but it's been fantastic for the community. So thank you, all of you. Selfishly, I'm particularly happy about this Women in Dispersive Day opportunity, because I could not come to the program, unfortunately, this year, but at least I'm here today, and I'm really happy about that. And also, let me say, although I've been in this country now more than about 30 years, and things have moved on from where they were when I first came, we still need women in occasions where women can have the spotlight, because so very often, even once you've become professor, even once you are, established and solid, and maybe you've won prizes or got papers, there's still something about being a woman that does not bring the spotlight so easily on you, and we shun it as well. So it's a bit of a two-way street, but it's great to have this. Is there a problem? Oh, you're screen sharing? No, I don't mind that. That's there.
No, just one. The microphone seems to be muted. But... Okay.
Oh, eagle eye. So thank you. I'm very happy to be here for the program, and to thank her. And I'm very happy to speak in the Women in Dispersive Day. And Barbara didn't read the second line of the title, but that is my excuse for being here. Dispersive PDEs meet discontinuities. It's it's not solid on gases, but you'll hear about them later. It's a very unexpected and quite fun phenomenon to talk about, and we have seen a lot of new things about it. So I hope it will be at the very least entertaining, and it has everything to do with being in the dispersive context. So hopefully it's not out of the theme of the day. Okay, so what am I? This is a question that really arises first from observation. It's so very rare for me as a mathematician and not a physicist to work out on something that for which the observation and reality are not far or five or six steps removed. It really was first observed in nature, this effect, and it was called later Talbot effect from the name of the first person that observed it. Then it went quiet. Nobody really wrote about it until much more recently, when it was also observed as a quantum effect, and it was called quantum revival. So now there are several names for this. I'll talk about it. And as a mathematical effect, so how to model this mathematically, it was revived. Well, really by Michael Berry in the 90s, though there were papers a bit earlier than that, focusing more on the analysis and regularity theory of these things. It's sometimes called dispersive quantization, and there is a reason for that name, which I hopefully will explain. But fundamentally, the question is this: dispersive PDEs, we usually start with humps, or in any case, smooth continuous profiles. What happens if you start with a profile that is not smooth? It has discontinuities, even just a step function, say, and that's the example to have in mind. You start with a step function with just one discontinuity, or maybe two also. If you consider periodic boundary conditions, it will be mostly periodic boundary conditions. What happens to the regularity of the solution? And it's a simple question, pretty natural also, because these things happen. And you can pose this question also in the nonlinear setting for our beloved dispersive nonlinear PDEs in one dimension. I will only speak in one dimension. It's not specific to 1D, but that's what I will talk about. And I will start, of course, from the linear problem, because in fact, let's start understanding what happens when we look at the linear problem, then think about the nonlinear. I will say something about that as well. Okay, so Talbot effect, this is just a little of historical context, but it comes from the name of this English eccentric polymath kind of guy of the 19th century, as there were many that were getting excited about all the new things that were coming on stream, as we would say now. But he was one of the first photography enthusiasts. He did many other things, but photography was one of the things he did. And he went around trying out this photographic apparatus, and he was taking photos like this one, which is very blurred, but it's the photo of a latticed window. Okay, and in fact, the earliest photographic negative we have is from one of these things, not this one, but something like this. And what he observed when he was observing light passing through these regular lattices on windows is that at regular intervals, the lattice, the light passing through would replicate the lattice, the grating, or maybe some number of copies of this pattern. And that's what he wrote extensively about, and what we call the Talbot effect. You know, he wrote, as you've seen, he was a member of, a fellow of the Royal Society, of course, as all these eccentric guys were. And fine, he was enthused by it, but nobody else seemed to have been enough to study it or to write about it until Michael Berry wrote a series of papers in the 96, this one, for example, where he put in a simple linear Schrödinger model to describe what happens. And these are the pictures from that paper that somehow show that there's a different, so if you start with a periodic grating, so an initial condition with some finitely many discontinuities, the solution will be discontinuous. Don't think about these vertical lines as anything but the fact that the resolution is poor on these numerics, but these are jumps at certain times, and no jumps, but very rough solution profile at other times. And he called this Talbot effect. And as I said, an analogous effect is observed also in the revival of electron wave packets. You can use Schrödinger equation, you know, free space Schrödinger to explain what happens. Anyway, it's an observation, it's an observed phenomenon. And so let me try to explain it or model it for you. Let's take this equation, and let's take an initial condition, U0, that from now on you should picture as a step function, but in general it could be a bounded variation with, you know, lack of, not continuous anyway. So I put together now several theorems due to several people to give a flavor of what happens. So let's say that U0 is a bounded variation. Then if you evaluate the solution at times, this is on the torus, so periodic on a 0 to pi or minus pi or something like this. If you evaluate it at a time, this is the time that is a multiple, rational multiple of the period. Here the period is 2 pi, it could be any period, and then it would be something. But anyway, a rational multiple of some constant that depends on the period. The solution is given by a superposition of the initial condition at finitely many translated points times some coefficient. We don't, you know, that's just fixed coefficient. In any case, it's just a superposition on a finite number of copies of the initial condition. So if your initial condition had a discontinuity, the solution will have the discontinuities inherited from the initial condition. That's just at these special values of the times. And this is a finite sum formula. You can just put it in a computer, you'll see, and I'll show you. But if otherwise, in fact, the theorem you can prove is that if T, the proven, actually, I say this, that if T is not in this special set of measure 0, the solution is continuous in X. Really, the theorem says that for almost all times, the solution is continuous in X. We certainly know that it is not continuous for those particular set of times, we really, it's not really very rigorously proved that these are all the times at which this happens, but I think that's true. And also, if U is sufficiently non-regular, so it's not in any Sobolev space for S greater than a half, say, so S equals 1/2 is BV, but if it's not regular, more regular than that, then for almost all times, the graph of both the real and the imaginary part of U is not just, it's continuous, but it's very rough. It has a fractal dimension, 3/2 in this case. Okay, so it's fractal means upper Minkowski dimension, but anyway, it's a very rough graph, but it's continuous. So no discontinuities for almost all time. So the discontinuities only appear in a set of measure 0 in the times, but they're observable, which is important. And as I say, there was the first paper on this is from 92, but it was really an analysis paper on proving this kind of regularity results. It didn't really speak of what happens at the rational time. That was first in these papers of Berry and then Rodniansky. Okay, so let me just show pictures, because one of the good things about this talk is that one can show pictures. This is just a continuous initial conditions, and you don't expect anything very much. It's a linear dispersive periodic problem. Nothing happens really. The solution remains continuous. It keeps moving about fine. So the initial condition here is blue, but at the beginning it has superimposed the real part of the solution. So it's that hump, continuous hump, and it stays blue in the others, and the solution, the real part of the solution is in red. If instead you have a step, okay, so the step is this, is the blue step. When you compute the solution, it's graphed and cut, just to take the truncation of the Fourier series. It's graphed with also the vertical lines, so it's a little bit misleading. There shouldn't be there. And neither should these vertical lines really be there. This is just an interpolation of the fact that you are truncating the Fourier series. But as you can see, if you take T multiple of this should be 5. Yes, they are wrong on the top. These are the times. These are multiples of pi, or of 2 pi if you want. You get the discontinuities, but if you take it at a different time, then it's, and that's not just for a step function. So we should see just a superposition of the whatever the initial condition was finitely many times at this special number of times. So if you take some very visually obvious initial condition, like a narrow box like this, then you see that at these special times, these narrow boxes are replicated all over the place, both in the real and the imaginary part. Here I'm graphing, or Dave, who is in the audience, is graphing both the real and imaginary part, whereas both the real and imaginary part get very fractal at all other times. Okay, so that's nice. And it was just done for linear Schrödinger until Peter Olver, and that's where I got in, was writing his PDE book and was trying to find exercises for his linear, his chapter on Fourier series. And so he took just the linearization of KdV, UT is UXXX, and was writing an exercise that said, find the solution to the periodic problem for this equation if the initial condition is just a step. And he graphed it, and as you would, he graphed it at these times first, and it's okay, it's a continuous function, but it did look much messier than he expected it should look. And so I don't know why, but he had the inspiration to look at it at multiples of the period, and he again saw this quantization at these times. And so he wrote this American Monthly piece. He didn't think that he thought this was just an odd and curious fact. And so he wrote this note on it and gave a talk, which I attended. And I got immediately interested because I have studied this equation with boundary conditions for a while. And I knew that boundary conditions were important. And I started thinking what happens if you take non-periodic boundary conditions, and I started talking to him, and that's how I got into this. And I will tell you what we did after this. But as you can see, so this is not a problem that's only, or a phenomenon that appears only when you look at this second order problem. It appears also for this other third order dispersive linear equation, if you look at the periodic problem. So in summary, these periodic revivals, as we like to call them now, is happen when at times equal to rational multiples of the period, essentially. The solution can be represented as a finite linear combination of translated and possibly reflected copies of the initial profile. So if you have discontinuities in the initial profile, they appear also in the solution at these times. And the theorem more generally that you can write is that if you have a dispersive PDE, a linear dispersive PDE of this form, and by writing it as I did with this coefficient psi, I just make sure that it is dispersive, and P is any polynomial with integer coefficients, then you can always write this representation. Actually, the proof is really simple. It's so simple that I will just tell you. In this form, the problem is written in this book by Erdogan and Tzirakis, who have pushed quite a lot the theory from linear to nonlinear. I will tell you later. But you can always write this representation as a sort of Gauss type sum. And why can you do this? This is the only proof I'll do, but it's cute. So let me try to tell you why this is true. Okay, so there are three fundamental facts. One is that if you have two integers that are congruent mod the q being the denominator of your rational multiple, then also the polynomials, if they have integer coefficients evaluated at those two congruent numbers, are congruent themselves mod q. And so you can write the Fourier series, which normally would be this times e to the minus I x m, and then the Fourier coefficient of u0, but you can bunch all the Fourier coefficients of on congruent integers together and write this as a infinite sum here. That's we call it T.
Beatrice, do you have assumptions on the degree of the polynomial? Or
No,
it's just a
no, just integer. Well, finite,
Finite,
but yes, any. It's completely generic of Fourier series, and the fact that the sum of all nth root of unities or qth root of unities in this case are, if it's either 0 or q. And so here I can add this sum equal to q if I divide by q. Okay, and I write it in this way by putting the e to the ij here on this side. And then once I do this is just q0 translated because of translation in the exponent. So it's nothing. Okay, the third ingredient is that the translation in x in physical space corresponds to a multiplication by an exponential in Fourier space. So it's completely generic, any degree and it's a simple proof. Okay, and if I just plot that finite sum instead of doing truncation of Fourier series or any other numerical game, this is what the solution looks like if you start from a step for A in this case. But so you see absolutely all these discontinuities. This is just the step replicated, scaled, moved about, but that's what it is. Okay, so that's periodic revivals, fantastic. What about fractalization? What do we know of the regularity of the solution at almost all times? Okay, so let me call them irrational times. They are almost everywhere, really. If you start from a solution with bounded variation, the solution is continuous, but the graph has a fractal dimension greater than 1, and we know it's 3/2 for Schrödinger, and it's in this interval 5/4 to 7/4 for Airy. And it depends on the degree of the polynomial, what the fractal dimension is. Okay, so that's just the theorem a bit more in detail, and that's okay. So if U is U is continuous as a function of the spatial space variable for almost all times, almost all in with respect to the bag, obviously. And if the degree of the polynomial, the dispersion relation is D, then U is actually a bit, if it's C alpha, we can say a bit more for all alpha less than 1/2 D minus 1. So for linear Schrödinger, for example, that's just a half because D is 2. And that's the BV space. And if U is not more than that, then the graph has fractal dimension in this interval. So again, if D is 2, that's just 3/2. It's 3/2 on both sides. And so what the solution has better regularity properties at irrational than at rational times. And really the proof is just number theoretical. It's not as simple as the one I just showed you for the quantization or for the revivals, but it really only depends on how you approximate irrational numbers by rationals. And then you can use regularity, non-regularity space. It's a lot more complicated and it relies on deep number theoretical results, but it's essentially a general proof. It doesn't depend on. Okay, so I will not go into that.
So, just sorry about this issue, right? So I assume that because not all irrational are created equal.
Yes, okay. So there are several, I didn't want to go into this. So there are lots of claims that, for example, if you take an algebraic number or a transcendental number, that the level of fractalization of there's no proof of anything. And we're actually working a bit on that right now, but we just started. But it would be very cool if not only your dispersive equation gives you a way to recognize rational versus irrational numbers. That's what number theory is like. If you could in any way also characterize algebraic versus transcendental, or for example, if you look at the infinite the representation of these numbers, how does that influence? Anyway, these are open questions. Although Rodniansky had some claims in his paper, but there is no proof about this. And you can certainly see more roughness in the solution when it's a bad number. If you take, for example, T is 0.1234567, it's fractal, but it's very self-similar. If you take pi or E, then it's not. So there's something there. Okay, well, that's my future. The past is that I really wanted to think about what about if you change the dispersion relation or you change the boundary condition, what happens? All in 1D, I haven't worked in anything else. So more general dispersive PDEs or non-periodic problems. And the question I will partially answer. So the first thing you can change is your equation or the differential equation. So for example, you put a potential on your Schrödinger equation. Okay. We wrote this for Dirichlet boundary condition. It's really like a periodic problem. Dirichlet on 0 pi, you double the interval and you get periodic. So it's really a periodic. It's just a little bit simpler to write. And this is work that just been printed, published. And U0 in VV. So we have a theorem that says that if V is in the H2, Sobolev H2, so that means two weak derivatives that are in L2, and U0 is VV, with some bound on V that is technical. We're sure it's technical because there is just a paper on Archive now that doesn't have that bound, and we see it numerically, but we couldn't get away from it if V is generally complex valued. If it's real valued, yes, you need much less. Then it's not quite true that you have these revivals, but almost true. So the solution at rational times, and here I'm only focusing on the revivals, not the fractalization. The solution at rational time has this same structure. It's a superposition of copies of the initial condition, but there is another term. The additional term is continuous. So for any V, even if it's in BV or, if it's discontinuous, because for real value, it could just be in BV, the discontinuities of the potential don't come into it. Okay, it's only this discontinuous initial condition. This term is continuous, so it will not breach these discontinuities. And we call this a weak revival effect. And to do this, we just analyze the asymptotics of the spectrum of this operator. So, okay, seems cute, but this is still periodic. What about nonlinear terms? And this is at first numerical, but and the numerics are due to my former colleague Katerina Schratz, who has a code that is robust with robust estimates for evaluating solutions of nonlinear dispersive problems, KDV, NLS, and all sorts of other things for low regularity initial conditions, because if you use the usual split step schemes and so on, they are not very reliable. They are only reliable for very short times. This is robust for very long times. And as you can see, if you start with a step functions or some box, you certainly see that a weak is not precisely, there are some, who knows, this may be Gibbs, but there are some slight perturbation of the profile, but it's certainly a kind of revival profile at the rational times. Same for KDV, even a bit more perturbed, but it goes up to relatively large times, and it's still very much the echo of the initial step is there. And so you might think, okay, and actually I should say for both NLS and KDV, this is now proved. So what you can prove is that if you split the solution into the solution of the linear problem that has the revival plus whatever is left, whatever is left is always continuous. And that's just hardcore estimations using Bourgain spaces and so on, but it's not very difficult. It's very technical, but it's not conceptually very difficult. So you can prove that it is a weak revival. Okay, there is the part of the solution of the linear part has this discontinuities. Whatever else is due to the nonlinearity is a continuous part. And so it's weak revivals for sure. You might think that that's due to the integrability of the equations. That doesn't seem to be the case. If you look at
Is for any amplitudes?
Well, I can.
The measure of nonlinearity.
I'm not 100%. I don't want to say. I think probably yes, but I'm not sure. I think probably yes, because you can put also strong nonlinearities, and this, at least for not very long time, still persists. So it seems to be a linear. It's a linear effect, and it's a very robust linear effect. It doesn't seem to. The thing is, as long as you can prove that whatever is left is continuous, even if it's very strong, it won't breach the jumps. So this is a non-integrable example where you still see. And then for out of curiosity, I asked her, can you show me what BO does? So Benjamin Ono is in the same hierarchy as KDV. It's one of our beloved water waves equations. I had worked on it for my PhD, so I thought, and it's integrable, so let's see what happens then. And when she graphed the solution of BO, this is what we saw. Okay, and this actually, before I knew of it, Peter Olver had a student of Peter Olver had graphed the solution of linear BO and saw something similar. So you see something special happening at these times, but it's not replicating that box. It's doing something different. And well, if you just look at the pictures, you don't really know what's going on. The reality is, as I now know, all of these cusps should really be infinite. There are discontinuity that are asymptotic at those points, but I didn't know any of this. It just looked different. So some time ago, Dave invited me and Peter and my colleague Lionel to Singapore when he was still in Singapore, and we decided to look at linear BO. And if you graph the solution. So you kill the nonlinearity, that's the equation there. H is the Hilbert transform, is what appears in the periodic Hilbert transform. I'll put it on. But anyway, let me say what the solution is. If you start with a step function and you evaluate it at these special times, you get these funny profiles. At regular times, you get something that it looks a bit more structured, but it's certainly continuous and very, very oscillatory. So we wanted to understand this, and we did write a paper out of that meeting that was out in 3 years ago or so. So we met in January 2020, just before lockdown. We traveled back when all the COVID cases were coming to the surface. So we had time to think about this problem when we went back. But really, we solved it when we were in Singapore. So this is the equation. That's one of the possible forms of the periodic Hilbert transform. I mean, you probably have in mind, if you know the Hilbert transform, you probably are more familiar with the expression on the line, which has G over X minus Y, but periodically, this is what you obtain. Really, it's much easier to think of it as a multiplier in Fourier space, and the multiplier is just the sign of the frequency you're at times I. And so the theorem that you can prove, and it wasn't so surprising, well, it took us a while to understand, is that at this special time, you don't just have a finite number of copies of the initial condition, but also a finite number of copies of the Hilbert transform of the initial condition. Okay, the Hilbert transform is in the equation. It seemed natural. And actually, I have a very recent result also. The fractal dimension at other times is also 3/2 in this case. So, but that's not published yet. But why these cusps? Because if you take the periodic Hilbert transform of a discontinuity, that's what happens. This is no PDE, this is just a function, which is the one in dotted blue, and its Hilbert transform superimposed on it. It just, wherever there was a discontinuity, there is a logarithmic cusp. Okay, this logarithmic cusp. The picture lies because these are really infinite cusps. Okay, really, I should have the asymptotes here and show that these are infinite cusps, but I'm not good enough with Mathematica to show it. Next time I give this talk, I'll just do it on the iPad, or maybe they will create pictures that are much better than mine. But anyway, so that's why you don't just see the jumps, but you see these cusps. In fact, mostly you see the cusps because wherever there is a discontinuity, there is a discontinuity, and the cusp wins. Okay, and in Singapore, we gave a really, well, in some sense, nice, but really involved proof. And it was really based on rewriting the solution, the Fourier series representation as a finite sum involving some special functions. And because Peter comes from it, Peter's father, is Frank Olver, was the man in special functions. Peter has a certain affinity with them. So when he saw the kind of expression we had, he immediately went to the digital library of special functions and looked around, and he found what special functions these were. They're called, I can't even remember, special logarithmic hypergeometric functions or some, or trigonometric functions. Anyway, you can find a lot of information about these particular functions in the digital library of special functions, what their derivatives are, what the discontinuities, their behavior. And so using that, we gave our proof. In fact, much more recently, we understood that there is a much easier proof that just uses this identity. The fact that for the Hilbert transform, if you just sum the positive part of the Fourier series, what's sometimes called the Zigo projection, this can be expressed in terms of the function itself and its Hilbert transform. And I'll say more about this, but fundamentally what you get is, okay, let's assume that this is just the mean of G. If the mean of the initial condition is 0, you can always do that. Then if you start with this initial condition and consider the solution of BO and of linear Schrödinger, they are related in this way. So all you know about Schrödinger, you can pass to BO without any special functions. Anyway. Okay, so that's another example of something that happens, but I haven't yet thought about boundary condition, and that was really what I wanted to study. What was my aim, was to change the boundary conditions and see what happens. Is periodicity really, really fundamental to having this effect, or is it something that is so robust that really survives also when you change boundary conditions? So they did a lot of that to check what happens if you have pseudo-periodic boundary conditions, and I won't show it. You can prove for linear Schrödinger that these revivals survive if you just do quasi or pseudo, well, for quasi-periodic and pseudo-periodic conditions with certain assumption it survives, but we moved also to look at something a little bit different, conditions that are not of Robin type, but really interpolate between Dirichlet and Neumann. Okay, if you take B1, that these are Dirichlet conditions. If you take B0, these are Neumann conditions. So if you take B1/2, they are periodic essentially, or quasi-periodic. So for B different from 0, 1, or 1/2, these are generally Robin condition, and we wanted to see what happens. And again, there is, if you look at the spectrum of this, all the spectrum is positive except for one eigenvalue, which is negative. And this negative eigenvalue adds a contribution. So let's call it T minus is the negative eigenvalue. So you have a part of the solution that's just as usual. That's a sum of translations of the initial condition, plus another part that depends on this unique eigenfunctions relative to the one negative eigenvalue. And this part, so everything in blue in formulas is a continuous function for me. Okay, so that blue part, the blue contribution is continuous. So this is just weak revival. Okay, but it's a weak revival where the continuous contribution is a bit stronger. Okay, so you definitely see the dichotomy, rational times, irrational times. But yes, there are discontinuities, but in between the step-like structure is pretty lost. That's both real and imaginary part. Still, okay, you see the dichotomy between these two. Qualitatively, is morally the revival effect survives, as does the fractal effect. Though we haven't proved that. We've proved this. Okay, not very difficult to track. Okay, so I'm about to step into the last part, which is the most recent results that are, in some sense, compendium of all these micro effects I've showed you. Weak revivals, cusp revivals, these logarithmic cusps, or no revivals, fractalization. So what we know so far, what we knew, let's say a year ago, maybe even a bit more, 18 months, for second order problems like free space Schrödinger, apart from the periodic case where we know everything, for non-periodic boundary conditions, if you have quasi or pseudo-periodic conditions, you still have revivals because you can always sort of open up and the interval and essentially go to a periodic problem. So it's like a periodic problem. But for Robin conditions is weak revivals. And if you add a non-zero potential also, you have weak revivals. However, revivals survive for all these cases. If you have BO and periodic boundary conditions, you move to a new manifestation of this revival effect in which discontinuities become cusps. And we wanted to go beyond that. So two problems that this is all for second order. For third order, I haven't told you, just the periodic problem we know has revivals. So we wanted to, first of all, I wanted to study more general boundary condition for the linear KdV problem. I would call it area equation. It's linear KdV in my book, but I was overruled. And also, Lionel suggested, my colleague, that we looked at a problem for the linear Schrödinger equations where you have a dislocation in the middle, and that's a problem that comes from cloaking metamaterials, all these sort of invisibility kind of problems, the simplest possible example of that. Whereas for me, studying the linear KdV eventually is with realistic boundary conditions is a way of maybe then saying something about real water waves. So these were, in some sense, far back motivated by real applications, because this is an effect also in search for interesting applications in my mind, which I believe exist. And so my question is, if I look at these two problems, which I will now tell you about more in detail, can I hope to see an echo of this periodicity and hence an echo of this revival property or fractalization or something? Okay, so that's the question I want to address in the last maybe 10 minutes, so we can get some questions in and a break. So that's the dislocation problem. That's the setup. So it's linear Schrödinger with plus or minus, so either positive or negative time, really, in two sections of this space. Okay, I've moved from 0 to pi to 0, 1. Apologies for that. It doesn't change anything qualitatively, but it does make the formula a bit simpler. Anyway, we did it on 0, 1. And then you have a Dirichlet boundary conditions are the two boundaries, x is 0 and x1, but there is also a special line in the middle at a point B, which divides the two sections where the direction of time in the equation is positive or negative, and you have this condition on it. So continuity across this location, but the first derivative changes sign. Okay, and as I say, this is a model for these metamaterials or cloaking properties. So what happens? Can we say anything for this? Okay, that's just the setup. And if you, well, it's not as simple to plot the solution because you can't evaluate the eigenfunctions and eigenvalues explicitly, but you can still sort of work around that. And these pictures are obtained by just truncating the Fourier series representation of the solution. And let me say, here, it's not very visible, but this is where B is. This is where the dislocation is. And the initial condition in this case has two jumps on the left of B. Mm-hmm. And you see then that whatever happens that is special, cusps or jumps or special non-fractal behavior happens only to the left of B. So only in the part where the initial discontinuities are, and nothing to the right. And if you evaluate at other times, only to the left, you have this fractalization that comes from the revivals, and nothing to the right. But if you have discontinuities on both sides, then you have the relevant behavior on both sides, but at different times, because the time depends on the length of the interval on which you are doing. And if B is not 1/2, these are two different lengths. So the rational times will be different values. So for a time that is rational for the left-hand side, you see jumps or something to the left and fractalization to the right, and the other way around. If you evaluate at a time that is rational for 1 minus B, for the length of the right interval. So that was interesting, but very unexpected. What's unexpected? Well, to hope that this dislocation divided also the revival effect so well. Well, that was a sort of wild speculation, but we didn't think it would happen. It happens. But we couldn't understand where this behavior comes from. We just didn't see just weak revivals, but we saw cusps. And there is no Hilbert transform inside here. So where do these cusps come from?
So these are finite cusps or also?
No, logarithmic cusps.
Does the initial data have to respect the discontinuity? So all of your initial data is flat, so.
Yeah, no, but that's just one. We have data that respect the initial condition, but even, here, these respect the initial conditions, but not always. This is just immediately the Fourier series will sort of regularize that. No, it's not so important. What was even more surprising is that if you take the third order problem, for example, with this set of boundary conditions, so Dirichlet, I call them of Dirichlet type. You have to give 3 boundary conditions now because it's a third order problem. So Dirichlet is the natural thing to do. And then you have to come up with a third condition. And the one that seems simplest and most symmetric, and in fact gives a self-adjoint problem, is to just take that the derivative is the same at the 2 ends of the interval. So this is, if you want, the simplest possible example of non-periodic third order boundary value problem that I could come up with. And you plot again, it seems simple, but you cannot evaluate the eigenvalues or the eigenfunction explicitly. So I knew this to begin with, but you also know that this is self-adjoint, so it has infinitely many positive eigenvalues, and there is a generalized Fourier series representation, and you can certainly evaluate it asymptotically. So we did, and these are the truncations of that representation. And you see, if you start with this step function, again, something happens at rational times that does not look like weak revival. This is not just discontinuities. There are this logarithmic type cusps. Again, please think infinity. These are discontinuities, but of just a different type. And at generic time, there is this very, very rugged profile. Very surprising. We knew from BO that logarithmic cusps appear when there is the Hilbert transform of a discontinuity, but there is no Hilbert transform here in the equation or in the boundary condition. So at first we were quite baffled. Okay, but really the answer is still linked in with the periodic Hilbert transform. And exactly why, well, this is just to remind you, this is what the operator version of the periodic Hilbert transform looks like on 0, 1. But if you write it in terms of its Fourier multiplier, what the Hilbert transform does, it takes the positive coefficients and flips the sign, and leaves the negative coefficient with the same sign and multiplies everything by I. That's so if f is the sum of f up n e to the 2 pi I and x, all with positive coefficient in front, the Hilbert transform reassembles the positive and the negative. But except for the I, okay, this is what it is, and from this expression, you can arrive immediately to this identity, which is crucial. Okay, it's crucial because it tells you that if you can write something in terms of just the positive coefficients, so if I can write my solution in terms just of the positive coefficients, then the Hilbert transform pops in sort of by magic.
Just letting you know, it's 9:50. That clock is just a little bit.
Okay, but I'm done. So this is really why the Hilbert transform appears. Okay, because when the boundary conditions are such that you can write all the negative coefficients in terms of the positive one and express the solution just in terms of the positive coefficients, and then you can use this identity. Essentially, I mean. Okay, so this was airy, just the boundary conditions that I said. No, let me just mention that, okay, so surprisingly, what we had seen was not just weak revivals, but weak cusp revivals involving the Hilbert transform of the initial condition, not of the solution, sorry. But I would like to say this is not true if instead of this third boundary condition, you decide, for example, to take this, which is also a pretty natural choice. You say, well, I'll stipulate I'll clamp on one end and leave the other free. No, this does not have, well, first of all, this does not have a basis of eigenfunction, so you're up against it to start with. But anyway, these are the only conditions of this type for which this theorem holds. Okay, and what is the theorem? The theorem is essentially that you can write the solution in two parts. One is this, and the other is just continuous, where U0 theta is just essentially the shifted Fourier coefficients. If these are zero, as they should be, these are not here, but if they're not zero, you put them in and they don't really change anything. And again, this is just by studying asymptotics of the eigenfunctions. But what's more important is that, so you see is a continuous contribution, that's the weak part, but this UR, which I wrote as an infinite series, you can really write as the sum of three terms that are all finite sums depending only on the initial condition. So it's the evaluation of the initial condition at certain translated points and of the Hilbert transform of the initial condition at certain translated points. So exactly like Bill, very unexpected. It was really quite unexpected. It's a lot more technical, but essentially it's the same. Morally, it's the same kind of phenomenon. And yes, these are the pictures. Here I have a bit more than I had before, just the initial condition, the exact numerical solution. That's the green is just this UR part, the part that is responsible for the cusps and jumps, whereas the orange is the continuous perturbation. And that's the fractalization result. Again, so the orange is just the difference between the exact solution and the part that we isolate. And the same happens for this model. That's even more technical, but we have a similar result. You can write the solution in two parts, a continuous part and a red part, which initially is this infinite series, but which depends only on the initial condition. On the interval 0b, you can write the same for the interval b1. This is forget that, it's not important. What's important is this part. And then you can manipulate this function UR to write it as the sum of, again, three terms, one involving the evaluation of U0 at translated point, the Hilbert transform of U0 at translated point, and some constant. So these are the pictures for that, and I'm closing. So this location in this case is here. The initial condition has one jump to the left, one jump to the right. Is it? Yes. And then you see that at times that are rational for the interval 0b, you have weak cusp revivals on the left and fractalization on the right, and times that are rational for B1, you have weak cusp revival on the right and fractalization on the left. The orange is the difference between the full solution, and the green, that's the revival part of the solution that it's essentially the leading order term of the asymptotics of eigenvalues and eigenfunctions. So very nice result, I thought, for a few reasons. And just to say, not everything works. There are some cases where we prove that there are no revivals. And surprisingly, of course, third order problem, if you have just a quasi-periodic problem for Airy, this is enough to kick the revivals away. They don't hold in this case. They do hold for quasi-periodic boundary conditions for the second order problem, but not the third. Okay, and the reason is that you can write the solution of Airy, UA, in terms of the solution of Schrödinger with a slightly modified initial condition at an irrational time. Because this theta, you can take it rational or irrational. If it is irrational, this is solution of Schrödinger at an irrational time for this initial condition. And this is just a translation. This gives you the solution of Airy. It's never revived. In fact, this tells you that it's not revived at rational times, but there are no other times at which it is revived. And this is just the picture. So it doesn't always hold. There has to be a constructive interference between the PDE, the boundary conditions, and it doesn't. It's a very delicate, but it's also very robust at the same time. Okay, so for now, this is where we are. Although, as I said, we did prove fractalization now for BO, and I'm working on the nonlinear problems now. But I do have a lot of questions that are open. So what is the regularity of the solution for these more general weak revivals cases? And like for Schrödinger with zero potential, and what happens when there is no rational irrational dichotomy? Why does the function look fractal then? You see, this fractalization seemed to happen up to the example of Airy only when there is this dichotomy. So there is some sort of lack of uniformity in going from an rational time to an irrational that creates all these oscillations. But there are cases where we see these oscillations, but there is no dichotomy. So I really don't understand. So I would like to understand. Are periodic revivals stable to stochastic perturbations? The answer seems to be yes. This is another thing I've done recently. And also, as I said, this is a problem in search of applications. Because although Kapitansky and Rodniansky wrote a paper in '99 that by the title, "Does a quantum particle know the time?" And this was about this quantum, well, the solution of linear Schrödinger recognizing rational and irrational number. Well, it seems dispersive waves know the time as well, and they might well differentiate even more sharply between also type of irrational. So that's another question, and I'll leave it with you. Thank you.
Thank you. I have a minute or two for questions. Marco?
Actually, two things. Did you try anything with second order in time? Let me also elaborate.
Wave.
So if you have linear.
Yeah, linear wave.
But maybe where the dispersion relation is actually not genus 1, genus 0 curve.
No, so we did the wave equation and it's sort of trivial. No, I don't know about higher genus, but
I mean, like the third order plus a linear order in X.
No, I haven't tried, because the second order in time and space doesn't really give anything. Just a Duhamel formula that tells you everything.
Second, the applications. What about cryptography?
Well, that's the obvious one.
Okay.
And yes, it's just very difficult to, talking to people that work in applied areas. Like I have even computer scientists in my building, but you need a lot of time to just get to the point where you start talking about science. So yeah, no, you need just infinite. So it's definitely the obvious one to try and look. And I think it might well have, because it's so robust. That's why I wanted to do this, to see if, because in reality you will need to have some certainty that if it's a little bit perturbed, it doesn't change things. But we absolutely know now that it's very robust, so it should be possible to do something in cryptography.
Just a quick, how important is the exact jump? If you smoothen the initial conditions slightly,
Well, if you smooth the initial conditions slightly, you will see that smoothing happen at rational. So you'll see. It's just that when you have a jump, it's easy to see.
Yeah.
If I plot the solution, you see the jumps happen at rational times. But the theorem tells you that for any initial condition at rational times, the solution is just a finite superimposition of whatever your initial profile was.
Mhm.
So if it's continuous, let's see, so it's just, it's not as interesting. If it's continuous, you just see something continuous. It's hard to see it up with your naked eye.
But it's a solid phenomenon. That
Yeah.
Okay, thank you
Sorry for
very
going
much,
over
Beatrice.
time. Thank you.